Hello, good morning, everybody. Good afternoon, depending on how long you've been up for. So last time we had a little bit of issues. I had an issue getting the slides open. I opened them before I started my Zoom meeting. I was a good teacher. So I have those accessible. So we'll open those in a second. We may skip through a couple of the slides or move a little quicker through them just because we already did scientific notation, or rather significant figures, but that's where we're headed. So let me go ahead and share my screen. Cool. All right, we are chapter 2. We're over here though. Okay. So just looking ahead, we're doing chapter 2 this week. Next week, we don't have class on Monday. And so we'll just be meeting on Wednesday for lecture. So we'll be doing chapter 3 next week and chapter 3 the following week. And then the Sunday after that will be your first test. Okay, so just starting to get yourself comfortable with the idea that in about just 2 weeks or so, you'll be having your first test. It'll be just chapter 1, 2, and 3. It's a good test to start off with. It's not intimidating or anything. So you guys should be fine. We leave the organic and the biochem stuff for the end when you're nice and warmed up. So chapter 2, chemistry and measurements. I'm trying to move this thing up. Okay, so identify place values, positive and negative calculations, percentages, writing numbers in scientific notation. Those are things we've already gone over. So units of measurement. So in science, you never really just write a number. You don't just say 58. Because that doesn't have any meaning for me. So we want to give it some sort of unit. Are we talking about 58 feet? Are we talking about 58 pounds? Are we talking about 58 students? So the unit of measurement is just as important as the number itself. So you're going to want to be sticking units onto your numbers. When you do tests and things like that, you will want to be, again, putting a unit to the number. Here are some of the common units that we find in the metric system. So AM, 8:30 AM, that's universal. But on this pleasant day out here, it's 22 degrees Celsius, which is equivalent to our 72 degrees Fahrenheit. We're going to be using Celsius in chemistry. So you're going to want to be able to convert between those two. We'll give you guys the calculations for that. But start thinking in degrees Celsius. This gentleman's backpack weighs 26 pounds. That's what we're used to seeing, but we're going to be dealing with grams and kilograms, so 12 kilograms. This person is 65 inches, which is what 65 inches is. This is why I hate the metric system, because inches, 12 feet. Okay, so she's 5'5", or 1.65 meters. Again, meter is going to be our unit of length. She weighs 128 pounds, but they would, the metric system would say 58.2 kilograms. And again, this, we could say these people have walked 1.3 miles or 2.1 kilometers or kilometers. We're going to want to start getting comfortable with meters, kilometers, grams, Celsius, those sorts of things. Why? Well, scientists use the metric system of measurement and have adopted a slightly modified measurement system known as the International System of Units. The International System of Units, or the SI units, is the official system that we use throughout the world for length, volume, mass, temperature, and time. A lot of countries use the SI units in their everyday as well, not just in their science world, because it makes a lot more sense than the British system, which is the pounds, feet, those sorts of things, gallons. So If we look at the metric versus the standard international unit, metric length is a meter, SI is also a meter. Volume is a liter, the SI would be a cubic meter. Do you see this here, how it's got an M to the third? So this is known as a derived unit. When we say derived unit, we mean that we got that unit from other units, all right? So when we think of a cubic meter as a volume, it's a meter length by a meter height by a meter width, okay? Meter by meter by meter. Mass, the metric is a gram, the SI is a kilogram. They've just put a prefix in front of it. The metric temperature is Celsius, the SI is Kelvin, and then second and second, okay? The difference between Celsius and Kelvin is just adding and subtracting 273. And we'll get into all those. So length, we use meters. There's meter, here we've got a centimeter as well. So here's a meter stick. 1 meter is equivalent to about 39.4 inches. A meter stick is just a little bit longer than a yardstick. So usually when you have like a meter stick, one side will be the metric side, the other side will be the yardstick. If we zoom in on some of these smaller tick marks, we can see that on the yardstick, we've got an inch here. An inch is roughly 2.54 centimeters. Okay. So these are some conversion factors. So annotate this. We call all these things conversion factors. Okay. All of these are examples of conversion factors. How many conversion factors are there out there? So many. Right? You can compare all sorts of different units to each other. What makes it a conversion factor is that it's one thing in one set of units that is equal to another thing in another set of units. So 1 meter is equivalent to 100 centimeters. 1 meter is equivalent to 1.09 yards. 2.54 centimeters is equivalent to 1 inch. There are a bunch of these, okay? So we will, you guys on exams and things like that, there will be a formula sheet that has a lot of these conversion factors. You will have to be able to use them, but you won't have to memorize all of them. But some of them will, you'll use so often, they'll just stick anyway. Volume, liters and milliliters. So volume always seems to be like a tricky one for people to get, but volume is this idea of space. How much space does something take up? So when we think of a liter is roughly 1.06 quarts. If you know what a quart is a quarter of a gallon. That's why we don't like the British system, because everything's all over the place. The conversion factors are all over the place. In the metric system, it's very precise. It's always an increase or a decrease of a factor of 10. So you get to just move the decimal place, which is really nice. So here we can see 1 liter is equal to 1,000 milliliters. 1 meter is equal to 1,000 millimeters. 1 second is equal to 1,000 milliseconds. That's the beauty, is that you get to just switch out the prefixes. That is not the case with the British system, with inches and feet and all that junk, so that's why we don't use it. Mass, grams. Kilogram is the SI. So just like we were talking about there being this consistency, right? 1 kilogram is equal to 1,000 grams. If you're wondering, well, what is a kilogram? It's roughly 2.2 pounds. And so you have a European friend that says, oh, I weigh 38 kilograms. And you're like, well, what does that mean? You would take their weight and multiply it by 2.2. They would weigh more than 38 kilograms. That would be really, really tiny. But they could say that they weigh 78 kilograms. So as far as grams are concerned, 1 pound has 454 grams. Again, each one of these things is a conversion factor. It's two things that equal each other with different units. Temperature in degrees Celsius and Kelvin. So on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit, right? So you know that if you look at the weather outside in the morning on a winter day and it's anywhere below 32, you know that there could be ice, right? Why 32? Such a random number. It has to do with the zero on that scale has to do with the freezing of a specific type of salt water. I don't know why they did it that way. That's just the way they did it. But in the metric system, when we're using, why does it, 32 degrees Fahrenheit, 0 degrees Fahrenheit again is the salt. So in Celsius, which I don't know why it doesn't have it on here, but zero, my annotation on. Come on. Okay, so 0 degrees Celsius, 0 degrees Celsius will be when water freezes, H2O freezes. You're gonna wanna know that. It's convenient though, it's right at 0 degrees. 100 degrees Celsius is when H2O boils. Okay, as far as when water boils in Fahrenheit, it's like 212. Again, seems like this totally random number. So that's why we like these here. Kelvin, or these K values are real easy. You just take your degrees Celsius value and you add 273. Okay, and that'll give you Kelvin. So let's say I had 4 degrees Celsius and I wanted to know what that was in Kelvin. I would just add 273 to it and I would get 277 Kelvin. What Kelvin does is it takes the degree Celsius scale and it shifts it over so that we don't get any negative numbers. There are a lot of calculations that you guys will do with temperature where you don't want to have negative numbers because it'll throw off the calculation. And if we talk about what temperature actually is, temperature is the measurement of the kinetic energy or the vibration that a material has. So you can't have negative vibration. It's either vibrating or it's hit 0. So absolute 0 or 0 degrees Kelvin is when we would expect all vibration in that material to stop vibrating, no more kinetic energy, which doesn't actually really happen. We just sort of like asymptotically approach it. All right, time is second. This one shouldn't feel too weird. So 1 second on the atomic clock. Boom, we got it. Okay. So here, so some of these slides have like little questions that we may do. Some of them will have like where you actually have to work it out. So I'll give you guys time to work it out and then we'll go back. This one we'll just go over. So identify the SI unit for each of the following. So volume, mass, length, and temperature. So the SI unit for volume is the meter cubed. The SI unit for mass is the kilogram. The SI unit for length is the meter. And the SI unit for temperature is Kelvin. So do know those, the SI and the metric units. There may be, your next test isn't going to only be on that, but there may be a question in there. It's an easy point to pick up, okay? All right, so we already talked about significant figures last lecture. So real quickly, we'll just go over, measured numbers are numbers obtained when you measure a quantity like height, weight, temperature. To write a measured number, you observe the number's values of marked lines. You estimate the value of the number between the marks. and the estimated number is your final value on the measured number. So looking at these three rulers, we've got 2, A and C are like crappier rulers. B is a more precise ruler. Okay, so for A, when I'm looking at the length of this stick, I put it against the ruler and I see that I go past the 1, past the 2, past the 3, past the 4. I don't pass the 5. So I know that I've passed the 4 mark. So I do put a 4. And then I, as an observer, get to guesstimate between the 4 and the 5. So what I'm seeing here is that there is, we're about halfway between the 4 and the 5. So I'm going to say we're at 4.5 or 4.5. This thing here, this ruler, allows me to have 2 significant figures. So 1 is definite. The 4 we know for sure. The 5 is an estimate. It's still significant, but the 5 is an estimate. So one of you may have put 4.5 reading this. One of you may have put it as 4.4 because you just read it that way, and that's okay. This one down here, same accuracy as this here. So we know we went past the 1, the 2, the 3. We hit the 3, so we know for sure we have the 3, but we haven't gone any farther towards the 4. So we kind of hit the nail on the head at this 3 mark. So we need to put that next guesstimate value in, because you're always 1 more precise than whatever your tick marks are. So we can always guesstimate 1 past this single digit value. So we're going to say that this is 3.0 because you hit it right on the head. 2 significant figures. Now this ruler in the middle here is a little bit more precise because it actually has tick marks in between our bigger numbers. So when looking at this ruler here, or this piece of wood here, I can see that I went past the 1, 2, 3, I went past the 4. I'm not quite to the 5, so I've got my 4. And then I can actually count that I've gone 1, 2, 3, 4, 5. So this number I know for sure. And then I can guesstimate between these ticks. So I'm somewhere between the 5 and the 6. Again, guesstimating sort of halfway between. So I'm going to go with 4.55. A little bit more precision here, so I get to have 3 sig figs. So whenever you're looking at these numbers, any measured value, the value all the way to the right is always estimated. That is always the case, okay? If a scale pops out this number for you, this 1 is estimated. The scale is estimating it for you, all right? So this we know for certain, this is an estimate. But we do include that in significant figures. So we would say that this number here has 1, 2, 3, 4, 5, 6. We're allowed to include 1 estimate in our sig fig. Any questions on that? I've sort of expanded a little bit on what we had talked about last time. Okay. So in measured numbers, the significant figures are all the digits, including your estimated digit. Here are the rules that the slides have. So all non-zero digits and zeros between digits, not zeros that act as placeholders before the digits, and zeros at the end of a decimal number. So looking at some of these numbers and their significant figures, right? These are easy. Whenever there's no zeros, it's easy. Just count all the numbers up. So here we've got 2 and here we've got 5. If there's zeros between, we include those because we can't be precise, imprecise, precise. We're a chunk of precision. So all 3 of those are significant and all 4 of those are significant. Zeros at the end of a decimal, we're going to say are significant. So like 25.0. So the writer of this is not saying, oh, it's sort of 25 degrees Celsius. They're saying, no, 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 it is 25 degrees Celsius to the tenths place. Like my thermometer is more precise, okay? And then we've got something like 16.00 grams, 4 significant figures, including the zeros, because they're telling us how precise that number is. It's not loosely 16 grams, it's 16 grams to the hundredths place. And then remembering zeros that sit in the front of your base number are not significant. We are just using those as placeholders to give us a scale on how big or small the number is. So scientific notation and significant figures. So scientific notation is when we write numbers in this way, right? We've got our decimal or our coefficient, and then we've got our exponent. So when one or more of the zeros in a large number are significant, they are shown clearly by writing the number in scientific notation. In this book, we place a decimal point after a significant zero at the end of a number. For example, okay, so let's say we have this number here, 300 meters. Looking at this number as far as its significant figures, if I was to write it like this, I could say that this 3 is significant. I don't know if the zeros are significant in the way that it's written. But if I was to change it into scientific notation, I could write it in this way and say, let's say that this 0 was significant. I could write it as 3.0, include just one of the zeros, times 10 to the 2. These numbers are saying the same things, but this one is preserving the significant figures. This one is arbitrary. So another example of that would be, let's say I end up with a number like 36,000. Okay. But this number needs to have, needs to be written in a way that has 4 sig figs. 4 sig figs. Okay. In this case, it's arbitrary, or it looks like there's only 2 sig figs. If I need 4 sig figs, I've got to be able to include those zeros. So the way I would write it is 3.600, 1, 2, 3, 4, times 10 to the 1, 2, 3, times 10 to the 4th. Okay, that's a way, a workaround if some of the zeros are significant and some of them aren't significant. All right, so zeros at the end of a large number without a decimal point are not significant, right? So this 400,000, we know that the 4 is significant. The rest of those zeros aren't, so we could write it like this. We have 850,000. Again, these zeros aren't significant. If we wrote it in scientific notation, the 8 and the 5 would be included. They'd be significant. Zeros at the beginning are just placeholders, right? If I was to take this number and convert it into scientific notation, I drop all these zeros in the front because I no longer need them because they're just acting as placeholders. Okay, so look at A, B, and C. I want you to tell me how many significant figures there are, and then I want you to write each of those numbers in scientific notation using the correct number of significant figures. Okay, so keeping zeros when you need to, not keeping zeros when you don't in scientific notation. All right, so 20 seconds here to just finish up your train of thought. Okay. So A here. We know the 2, let me put my annotation. We know that the 2, the 6, the 5 are significant. This 0 is also significant. It comes after the decimal place, after the base number. It is included because it's telling us the number is precise to that. These zeros in the front are not significant, okay? So this thing should have 4 sig figs. That means that when you write it in scientific notation, it should also have 4 significant figures. So here's the decimal. I'm going to hop it over 1, 2, 3. So I should write it as 2.65, and I include the 0, okay? Because the 0 is telling us precision. 1, 2, 3, 4 sig figs. Oh, then we have to put the exponent, right? Because we just made a really small number look bigger than it actually is. So times 10 to the negative, and we took, what did we say, 3 hops? 1, 2, 3, 3 hops, okay? So 2.650 times 10 to the negative 3. Are there any questions on why we're including that 0? We like that 0 because it's letting us know it's precise. It's included over here, so we carry it with us. We don't include the zeros in the front. All right, this guy here, all those are significant. 1, 2, 3, 4, 5 significant figures, okay? 5 sig figs. This is a number that I wouldn't necessarily write in scientific notation because it's going to take more work, but we're going to write it anyway. So 4.3026 times 10 to the 1, right? 1 hop. The decimal was here. We hopped it over here. Last guy down here. Oh, and I'm being bad right now. Let's include our units, meters and grams. Okay, so decimal lives over here. It's invisible though, which means we can't include these zeros as significant. So the 4, the 4, the 1, and then the 0 in between are significant. So you should have gotten 4 sig figs for this. The decimal lives here. To get it in scientific notation, we need to hop it 1, 2, 3, 4, 5, 6 hops. 1.044 times 10 to the, we're going to do a positive 6. Why? Because we just remember that this is a big number, so we want it to be positive. 4 sig figs there, just like there are 4 sig figs there, and I'm going to add a unit of liter. Yes, you like? No, don't like? Okay, cool. Great. All right, so then the slides go through and explain everything we already talked about. Okay, so one situation where we don't deal with significant figures are when we're dealing with exact numbers. Because what is a significant figure? It's telling us how precise a number is. Well, when you're counting discrete objects or you're dealing with integers, that's not a measured value, right? 12 eggs, you didn't have to like use a piece of equipment, you just counted them discretely as 12. So anything that's not measured does not have a limited number of significant figures. Doesn't affect your calculations. So when we were talking about significant figures, if you're multiplying, dividing, or adding and subtracting, we would not use our lowest number of sig figs as an exact number. So like these conversion factors here are infinite number of sig figs. They don't limit our calculations. And that'll make a little bit more sense later on when we do some calculations. So numbers obtained by counting and then comparing 2 units, yeah. So 8 cookies, that's not like a precision thing. Like Colleen isn't gonna be better than Haley at counting 8 cookies. Hopefully both of you guys can count 8 cookies. Unless they're a special kind of cookie, then maybe they're not 8, but you know, there'll be 8 cookies, okay? So, or 6 eggs. There's not room for interpretation. There's no value of guesstimation with that, or you can't get like more precise. And you're like, well, I use my right eye, so I'm more precise with my 6/8. No, I mean, it's a discrete object. So no sig figs there, just with measured values. All right, more examples of exact numbers. 8 donuts, 2 baseballs, 5 capsules. Any of these conversion factors. For the sake of this class, conversion factors have unlimited sig figs. So what that's saying when it's saying unlimited is, like if I look at this one, one foot, where are you? 1 foot equals 12 inches. What I'm really saying is like 1.00000 zeros all the way to infinity, okay? So it's like the most precise 1 foot you've ever had is equal to 12.0000 all the way to infinity inches, okay? So those have endless significant figures. Great. Identify the numbers below as measured or exact and give the number of significant figures. So I'll just walk through these real quick. Okay, 3 coins. That is a exact number. We don't have half coins, we have 3 coins. So this would have unlimited sig figs, or you could also say it doesn't have significant figures. There's nothing as far as precision is concerned there. B, the diameter of a circle is 7.902 centimeters. Anytime it's a measured value, we're going to say that that has significant figures, or it's a measured value, 1, 2, 3, and 4 significant figures. C, down here, this is a conversion factor, 2 things that equal each other. 60 minutes equals 1 hour. That is going to be exact. It's a definition. I mean, what makes an hour is that it's 60 minutes. What makes a minute is that it's 1/60th of an hour. So significant figures and calculations. Did we talk about, sorry, all of my chem classes start the exact same on this information, so I get crisscrossed. Did we do calculation sig fig stuff? Like what you do if you multiply, divide, add, subtract? You can just put in the comments, no, who knows? I wasn't paying attention, maybe. Let's see, what's the chat got for me? Not yet. Yes. One person says yes, another person says not yet. Okay, so we'll
I think you were just telling us where it was on the calculator. You were just showing us what we started and then ran out of time, I think.
Okay, so we'll just do it again. Why not? Even if we did, we'll just do it again. No problem. Cool. So significant figures in a calculation. So a calculator is helpful in working problems and doing calculations faster. Yes, it is. You will want to have a calculator available throughout this class. Let's talk about rounding really quick. And this is going to seem silly, but we definitely don't want to lose points because of rounding. So if the first digit to be dropped is 4 or less, then it and all the following digits are dropped from the number. If the first digit being dropped is 5 or greater, then the last retained digit of the number is increased by a factor of 1. So kind of 4, if it's 4 or lower, you round down or you stay. If it's 5 or up, you round up. You're like, this sounds really complicated, but it's not complicated. So if I have 3.82 and I want to round this to the tenths place, the 2 tells the 8 to stay, we would get 3.8. Okay, basic rounding. 4.5, let's say we wanted to round it to the ones place. The 5 would tell the 4 to round up. This would become 5. Okay. So basic rounding. We look at some of these examples. So let's say we have this, let's say your calculator filled this number out here, 8.4234. But only 3 of those numbers are significant. That means you have to drop everything else. So how do you do that? Well, you start all the way to the left and you go, okay, I get to have 3 sig figs. So I get to keep my 8, I get to keep my 4, and I get to keep my 2. Everything else has to get dropped So the 3 will tell the 2 to stay where it is. We end up with 8.42. If we decided instead to round to 2 sig figs, I'd get to keep the 8, I'd get to keep the 4, everything else gets dropped. The 2 tells the 4 to stay, we'd get 8.4. Looking at this guy here, 14.780. If I want to do 3 sig figs, I get to keep the 1, the 4, and the 7. The 8 tells the 7 round up. So we'd get end up with 14.8. The 8 and the 0 will get dropped. If we had to do it to 2 sig figs, we would get 15. Why? Because the 7 tells the 4 to go up to the next number. Here, this is important. So I've got 3,256. If I'm going to round this to 3 sig figs, I get to keep the 3, the 2, and the 5. I drop the 6. The 6 will tell the 5 to go up to a 6. But this does not become 326. You can't lose the size of the number, right? This is in the thousands. So whatever you drop, in this case, you have to fill it in with a 0. All right, so we wouldn't round this number to 326. We'd round it to 3,260. All right, so drop the 6, add the 0. If we did 2 sig figs, I'd get to keep the 3 and the 2. The 5 would tell the 2 to round up to a 3. And then again, we'd have to fill those in with zeros. So I'll give you like a real big number. So let's say we have 3,841,256. And let's say I have to round this to 1 sig fig. This is a big number, all right? So my rounded number should also be big. It's just going to be less precise. So what do I get to keep? I get to keep the 3, and that's it. So the 8 tells the 3 to go to a 4. But again, when we round this number, it doesn't just drop to 4. 3,841,256 for 1 sig fig rounds to 4 million. Okay, we've got to fill those zeros in. Great. So looking at this number here, 3.1457, I want you to try and round that to 3 sig figs and 2 sig figs independently. Okay, so first one here is saying, let's do it for 3 sig figs. So if we're doing for 3, I get to, again, start counting from the left hand. I'm not sure if it's mirrored on there, but the left-hand side. So we start at the 3. So we keep him, we keep the 1, and we keep the 4. You can put a line or something to let yourself know that that stuff's getting dropped. You only use the 5 to tell you what the 4 should do. The 4 should go up. So we should end up with 3.15 when we're, and I'll put a G there, when we're rounding. Two significant figures. Okay, so that means, just change color here. Two sig figs, we get to keep the 3 and we get to keep the 1. We look at the 4. What does the 4 tell the 1 to do? To stay. So we get 3.1 grams. That's it. Now, sometimes I get students asking, well, if I'm doing 2 sig figs, can I have the 5 tell the 4 to go up to a 5? And then the 4, that's now a 5, tells the 1 to go up to a 2. Don't play that game with yourself because it could go for a very, very long time. Like this number, 4.449. If I'm rounding this thing to 2 sig figs, 4, the 4 tells the 4 to stay. This is 4.4. You don't have the 9 tell the 4 to go up to a 5, and then the 5 tells the 4 to go up to a 5. Why? Because like, how far back do you want to go? What if you had a number like this, 4.4, 4, 4, 4, 4, 4, 4, 9, and you want 2 sig figs? Do I have to go here and make this 5 to make this 5 to make this 5 to make? No, we don't do that. Okay, we just look at the number that's getting dropped, the leftmost number. Good with that? Yes, like that? Cool. Okay. So going back to our, like, what is it, like 3rd grade math skills rounding, but yeah, you forget the stuff sometimes. So, okay, we'll skip through there. So when you guys are running calculations, and like 90%, 95% of the calculations you guys are going to be doing in this class are going to be multiplication and division. There'll be some addition and subtraction and maybe like a log here or there, but it's really going to be mostly multiplication and division. So if you have 2 numbers and you are multiplying or dividing them together, and you end up getting this like really long number in your calculator. You've probably had this happen before in math classes where you get this really long number and you're like, how many of these numbers do I use? There is a reason and a specific amount of numbers that you're supposed to use. You always go for multiplication and division with the lowest number of sig figs on the given information. Okay, so if we look at these 2 numbers here, I have 24.66. This has 4 significant figures. This one over here, 0.35, has 2 significant figures. So when we're talking about precision, this number is pretty precise. This one isn't quite as precise, right? Your final answer can only be as precise as your crappiest piece of information. So if you have a crappy measurement, your final answer is also crappy. And it has to be the same amount of crappiness. So this has 4 sig figs, this has 2 sig figs. The calculator ends up displaying this thing, sorry, which looks precise. We only get to use 2 sig figs. All right, so we've got to drop the 3 and the 1. We end up with 8.6. So if you're ever wondering when you're running through these calculations, how many of these numbers am I supposed to keep? You keep multiplication, division, the lowest number of sig figs. And some people that really bothers because they get these really long numbers in their calculator and it's like super precise and they go, I want to use every single one. I like all these numbers. Well, you can't. Okay? You can only use some of them. Let's look at this one here. So let's say we're taking 21.5 times 0.30 divided by 1.88 centimeters. So we take this number, we stick it in our calculator, and we get this like huge number with all these decimals. Oh my gosh, my number is so precise. Well, all of this is sort of junk information. You can't use it. This first value has 3 sig figs. This second value has 2 sig figs. The last value has 3 sig figs. Again, you're only as strong as your least precise piece of information. So you have to go with the lowest sig fig. That means I can only use 2 sig figs here. So I get to keep the 3. I get to keep the 4. Everything else has to go away. 3.4 centimeters. So hopefully that gives you a little bit of a better idea when you're using a calculator, like what numbers are important and what numbers aren't. We'll do some practice with that too. Oh, here's another one. Adding zeros in case you need to do some, increase your precision, okay? So plug this into your calculator. Take 6.0 and divide it by 2.00. So those are both measured values because they have a decimal. But when you divide that out, what does your calculator display? It displays a 3, right? Because you're pretty much taking 6 divided by 2. So what we can see here is that we had 2 significant figures, we had 3 significant figures, and the calculator sticks it out with only 1 sig fig. We can't keep it as just 1 sig fig. We need to make sure that we expand this out so that it represents the number of significance. So this has 1 sig fig. I need to make sure it has 2 sig figs. The fastest way to do that is put a decimal and add a 0. All right. When this number is written like this, it now is represented with 2 significant figures. So we're keeping the precision. So on occasion, you may have to do that. It doesn't usually happen. Usually you get a bunch of decimals, but if it happened to come out where your final answer had less precision than your initials, just add some zeros, decimals. Okay, so try this one, stick it in your calculator, and then I want you to round it to the correct number of sig figs. And you can use your phone calculator too. Okay. So the calculation itself isn't that challenging, right? We just put it in the calculator. The test, you know, because you may get 1 or 2 of these on an exam and you're like, this is just basic math, but the key is that you're getting the correct sig figs, all right? I will tell you as the semester goes on, my care for sig figs decreases, okay? But on this first test, obviously it's like there's a chapter about it, so make sure you know how to do them. So when I plugged this into my calculator, I got 8.52. And it's what, a centimeter times a centimeter divided by a centimeter. So the units cancel, so the unit would just be centimeter. So 8.52 centimeters. This has 3 sig figs, this has 4 sig figs, this has 2 sig figs. I only get to honor 2 sig figs. So I'm going to cut that 2 off. The 2 tells the 5 to stay a 5. So we get 8.5 centimeters. Do you know when the first test will be? We'll talk about it at the end of class. We'll take a quick peek at the syllabus together so we can plan forward. Questions on this? No? Okay. So answer needs 2 sig figs. Right, so why would you write 3 sig figs, slide? When you're looking at these slides, you ignore that 2 right there, okay? Because this is 2 sig figs. What they had written was 3 sig figs. Who knows? Sometimes these slides are a little goofy. So hopefully this is feeling easy. I want it to feel simple, and then, you know, we just sort of build from there as the semester goes on. With addition, subtraction, you follow a different set of rules, all right? So in addition, because multiplication, division are like equal and opposite order of operations, right? They're the inverse of each other. Addition, subtraction are at a lower level of order of operation, but they're equal and opposite of each other. So in addition, subtraction, we follow a different set of rules. Instead of the lowest sig figs, we follow the lowest decimal places. How do you know how many sig figs you need to do again? For that last one, so again, here, this should be, we don't, sorry, give me 1 second, guys and ladies. This we don't want here. How do we know? Because this has 3 sig figs, this has 4, and this has 2. We always go with the lowest number of sig figs, 2 sig figs. I don't know why. This is just going to confuse people, but that shouldn't be there. Okay, cool. And if you ever have more questions after anyone's ever like, I'm not sure about that too, but I don't want to ask now, just make a note and you can talk to me after class about it as well. Okay, so addition, subtraction, you go with the lowest number of decimal places. So we don't worry about sig figs with addition, subtraction, we do decimal places. So what you can do is write, remember when you used to add and subtract like old school like this in 2nd grade and you'd line up your decimal? That's maybe how you want to do this, because then it becomes really easy visualize what needs to be dropped. I can see this has 3 decimal places, this has 2 decimal places, this has 1 decimal place. I am only going to be able to keep 1 decimal place. So you add those together, the calculator will display 66.102. Because this is my least precise piece of information, I'm limited to 1 decimal. So I just keep the 1, the 0 tells the 1 to stay a 1. Same thing with subtraction. So again, you can write it old school like this, lining up your decimals. Stick a line right. So hard to annotate on these slides. Stick a line right down there because this is the weakest piece of information. I know I'm going to have to truncate that last 9 at the very end. So the 62.09, the 9 will tell the 0 to become a 1. All right. I do think it'll give us an example. Okay, so try this one. So add these 2 numbers together and then round it to the appropriate number based off of decimal places, because we don't do significant figures for this. All right, so simple, plug it into your calculator and you get a number. In this case, I got 104.409. This number here, ooh, that's a really nice piece of information. It's like real precise. This one here, not as precise. So that means we've got to drop some stuff. We only get to keep 1 decimal. So we get 104.4 because the 0 tells the 4 to stay. And this is units of milligrams. You notice this thing has 4 significant figures. This thing has 3 significant figures, or rather, I'm sorry, this has 5 significant figures. This has 3 significant figures, and this thing has 4 significant figures. Significant figures don't come into play when you add and subtract, all right? So if you're getting a different number of sig figs with addition and subtraction, that's okay. It can happen. Okay, great. So let's see. Yeah, we've got a little bit more time. I want to keep going. All right, so prefixes and equalities. So this is one of the beauties of the metric system that we had talked about earlier, or the SI system, where we use things like meters, liters, seconds, grams, those sorts of things. Joule we can use as well. These are considered sort of the base unit. And so if we want to make that value bigger, we can just add a prefix to it, like a kilometer or a kilometer. If we want to make it smaller, we just add a smaller unit, like a millimeter. And those can get plugged in, sort of like Legos. You can stick them into different units when you need them. So some examples of prefixes they've got here. These are smaller units. So a milligram is 1,000 times smaller than a gram. A microgram is 100,000, or is 1,000,000 times smaller. A microgram is 1,000,000 times smaller than a gram. So real nice there. You can see when looking at the name, there is the base for each of those. It's a gram. This is the prefix, pre coming before. We get to plug it in. When it's written in its shortened form, you always put the prefix symbol first and then the base unit, gram. Here's a micro, or sometimes it's written like that, and then we've got our grams. So some prefixes that are larger than the kilo. So there's the symbol for it, numerical value, it's 1,000. So it's 1,000 times greater than whatever your base unit is, or 10 to the third. A mega, like back in the day when, you know, our cell phones used to have like 2 megabytes of space. Right now, that doesn't really mean anything. That's it's 1,000,000 times bigger. Now we work more with gigabytes, right? So when you get a new iPad or a new iPhone, you're like, I want 128 gigabytes. Some of you guys may be real computer savvy and have like a hard drive at home that's got like a terabyte to it. And that's going to be 10 to the 12th, right? Or what do we have? A giga is 100, 1,000, million, billion. This is a trillion. So. Here are some smaller prefixes: deci, centi, milli, micro, nano, pico. Pico is really teeny tiny. Pico is like equal opposite in the other direction of your tera. We will spend most of our time in this sort of milli to kilo range. You may see micro a little bit, so know those. So let's take a break here, or not a break, but let's go over to dry erase because I don't think they have it. They don't have King Henry. And I like King Henry. I think it is helpful. So if you were in my class before, you already know King Henry, but I'll teach everybody else. I feel like, what is this lady talking about? I'll show you in a sec. All right. You've got to go up there. Okay. So King Henry, I'm going to write this out, died before drinking chocolate milk. Okay. King Henry died before drinking chocolate milk. You may have heard this as King Henry died drinking chocolate milk. I like to put the before in because that's our base unit. So let's start there. B is for your base unit. Examples of base units: gram, liter, meter, second, joule. The died, the D for died is your deca. Okay, deca. Your H is your hecto. That's not one we use a whole lot. Your K we use a lot. That's your kilo. So we've got our base unit, we've got deca, hecto, and kilo. If we go over towards the right, the D on this side is your deci. Your C is your centi. And your M is your milli. So that's one way to remember at least the ones between kilo and milli. There are some that are smaller and there are some that are bigger that you may have to work with, but at least to have like really quick movement between these, this will help. So let's do some basic conversions because because everything is a base 10, we get to just hop decimals when we're wanting to convert. So let's say that you told your roommate, you were like, I went out this morning, I was like really good, and I went and ran 0.037 kilometers. And your roommate's like, I don't really know what that means, but that doesn't sound like that big of a deal. How many meters is that? Okay. So your roommate's saying, well, tell me it in meters, because I know a meter is like roughly 3 feet. So like, tell me how many meters that is. Okay. So the way that you can use this system, it needs to be written like this. Don't write it backwards, write it like you write it in a book. Okay. So we're starting with a kilometer or a K. So we are going to put a little asterisk here because we're starting at king. We want to get to meter. Meter is an example of a base unit. So we want to move over here. Okay. So in order to do that, I need to leapfrog through all these things. So I'm going to hop 1, 2, 3 spots. Specifically, my decimal is going to hop 3 spots to the right. You go in the same direction that you're hopping. So if my decimal's here, I'm going to hop it to the right 3 spots. 1, 2, 3. And now your decimal lives there. So you can now tell your roommate that you ran 37 meters. Not quite as impressive, right? Your roommate may say, oh, well, that's like halfway down the block. Good job. Maybe next time try and go a little farther. But a real easy way to switch through. We can go in the other direction too. So let's say I'm, do this one in red. Let's say that we're given that we have 38 million millimeters. And I want to find how many kilometers that is. So the millimeter, look at the prefix, that's your milk, all the way on this side. We got to get all the way over to kilometer over here. So we need to hop 1, 2, make sure you hop through the base, 3, that's why I put before in there, 4, 5, 6 hops. Where is the decimal here? It's living right there. We need to take 6 hops in that direction or to the left. So 1, 2, 3, 4, 5, 6. We know that we have 38 kilometers. Isn't that nifty? Can you do that with the metric or with the British system? No. If I say, hey, I've got 80,000 feet, how many miles is that? You're like, I have no idea. What is that conversion? Ugh, how many feet are in a mile? It's like so hard to remember, you know, they're all different. There's 12 inches in a foot. There's 3 feet in a yard. There's 5,280 feet in a mile. It's like none of them relate to each other. But here, everything is on a base 10. So we just get to hop decimals around. And that doesn't just work for meter. It works for like gram too. So let's say, why won't you go away, you little thing? Because it's recognizing it as a shape. Okay, well, we'll just use it. So let's say that we're given that we have 300.1 grams. And I want to find kilograms. Okay, we're not in meters anymore, but it's okay. The base unit for this is going to be our gram. Change color. So we're using this thing here. Let's make that a little narrower. We are starting with the base. We need to head over to the K. So we're going to hop 1, 2, 3. I take my decimal, I hop 1, 2, 3. 3. So 0.3001 kilograms. Super nifty. Fast way to jump between those. Some people remember it as, oh, there's 100 centimeters in 1 meter, and there's 1,000 kilometers or there's 1,000 meters in 1 kilometer. You can do it that way as well, but this is kind of just a fast, simple way to move around. Okay, so what we're gonna do now, I'm gonna stop sharing my screen here. All right, I'm gonna break you guys up into some breakout rooms. I don't know if you've done that in your other classes or not, but what it's gonna do, like the computer is going to, or the system's gonna prompt you to join a room, a separate room. And there'll be, I'm gonna do 4 per room. So you guys can introduce yourselves to each other and you can get each other's information, okay? So that you have an email with a face to somebody else in the classroom. In case you're having trouble on a lab, you can, email Ashley and say, oh, Ashley, hey, we chatted for 3 minutes that one day. Can you help me do this lab? Because I don't know how to do it, okay? So if your camera is off, I'd ask you to put on some clothes now and and meet a couple of your students in your class. Hello. Awesome. Okay, so we're gonna do that right now. Don't trash talk while you're in there about me because I may hop in and say hello. Let's see. All right, breakout rooms. So there's 32 of us. 32. All right, so we'll do 8 rooms. 32. All right, it should start prompting you all.